Hello, pre-calculus students. Today we are going to start talking about chapter 7, which is about identities. So you'll need something to write with, maybe some highlighters, you'll need your 7.1 notes, and you will need your unit circle. Okay, be sure that as we're working, I'm going to get you started, but you should really start to, make sure you try them on your own. Maybe watch the video a little bit for a hint if you're getting stuck, and then pause it back again, and then start rewatching. Okay, you'll find with this section and the next section, all the problems look kind of different. And so sometimes you might not be sure how to start them. The more you do them, the easier it will become. But at first, you might feel a little bit overwhelmed and like you're not quite sure what to do. So, like I said, maybe watch a little bit, get a hint, and then try to keep going from there. And then, keep going back and forth that way until you get what you need. Okay, so let's get started. So we're going to start out by talking about some basic trig identities. And these identities are actually on the back of your unit circle. So if you look on the back of your unit circle, you'll see it's on the left side. It says trig identities. On the right side, it has some stuff about chapter 12. Okay, so we're going to be talking about a lot of these identities. We're going to talk about some of them today. And as we progress through the chapter, we'll talk about more and more of them. So you're going to want that in front of you. So to start, when we talk about these identities, that means it's a statement that's true for all values of the variable. And you played around with that a little bit last chapter when you were doing the inverse rules. And is this always true? For what values is it always true? Okay, so a statement of equality between two expressions that is true for all values of the variables for which the expressions are defined is called an identity. So the first thing we're going to talk about is, well, what if it's not true? So if you can show a specific value of the variable in an equation that makes the equation false, then you have produced a counterexample. It only takes one counterexample to prove that an equation is not an identity. So if it doesn't work for one value, it's not an identity. Now, it has to work for every value in order for it to be an identity. Okay, so we'll use variables if we're trying to prove something is an identity. Okay, proving an equation is an identity requires showing that the equality holds for all values of the variable where the expression is defined. Okay, so for this first one, it's asking you to prove that the sine of x times the tangent of x equals the cosine of x is not a trigonometric identity by producing a counterexample. So when you produce a counterexample, and again, we did a little bit of this last chapter, you're going to pick a value to try, and you want one that makes this not work. So you're going to pick a value from your unit circle. And you could pick anything you want. Now, if it ends up that it does work, we're trying to prove this is not an identity, then you would need to try something else. Okay, so you can pick whatever value from the unit circle you want to use and then try it. Okay, so go ahead and pick a value, plug it in, use your unit circle to evaluate, and then it should come out to be false. If it doesn't, you have to pick something else. I'm going to pick 30 degrees. So I'm going to let x equals 30 degrees. And I'm going to substitute that 30 degrees in everywhere I see an x. I'm going to put a question mark over the top of this equal sign because I don't know if this is true or not. I have to try it out. Okay, so sine of 30. I'm going to look at my unit circle. Sine of 30, that's my y value at 30. So if you picked a different angle measure, you would use whatever the sine value is at that angle measure. So I have 1/2 times the tangent at 30, which is root 3 over 3. And I want to know, does that equal the cosine of 30, which is root 3 over 2? And so if I do this multiplication, if I multiply across the top and the bottom, those are not equal. So this right here is a counter example. Okay, here's my work to justify that it doesn't work. Okay. Now, I think if you had chosen something like 45, because the sine and the cosine are the same, and then the tangent of 45 is 1, that actually would have worked. So if you would have tried one of those multiples of pi over 4, it would have worked. So you would have to try something else. Okay, example 2, it says use the given information to find the trigonometric value. We did this a little bit back in chapter 5. Okay, and so this goes back to remember cosine and secant are reciprocal functions, and sine and cosecant and tangent and cotangent are reciprocal functions. And if you look at the back of your unit circle, you'll see that's there as a reminder up here in the top, right? Sine is 1 over cosecant, cosine is 1 over secant, and so on. Those are all there. Okay, So, well, I know that these are reciprocals of each other. So the secant of theta is just, I can just straight up take the reciprocal of what I was given for the cosine. I don't really need to do a whole lot with that. All right, so now in the next one, I'm given that the cosine is 3/5, and I want to find the cosecant. Well, there's not a direct relationship between cosine and cosecant. And so then this is where I would draw a right triangle, sort of like what I was doing back in chapter 5. So I'm going to draw a right triangle. I'm going to label my angle theta somewhere on there. It doesn't matter which of these acute angles I label it. But if this is a cosine ratio, then I know the top is the adjacent and the bottom is the hypotenuse. Okay, adjacent would be here. Hypotenuse is always across from that 90-degree angle. So this is 5. That makes us a 3, 4, 5 triangle. So if I want the cosecant, cosecant is the reciprocal of sine, and sine is opposite over hypotenuse. So that means cosecant is hypotenuse over like opposite. So my cosecant would be 5 over 4. And again, that goes back to something we had done back in chapter 5. All right, now we're going to get into this identity stuff. And so we're going to be asked to simplify each of these expressions. So when you look at them, you'll see they're a combination of sines and cosines and secants and cosecants and tangents and cotangents, and we want to simplify them. We're going to be using those identities to do that. Okay, as we go through the next couple of lessons, there are going to be some tips and tricks that kind of will make this easier. My first one, and this is kind of the fallback if nothing else works, is to rewrite everything in terms of sines and cosines, if it isn't already. So rewrite everything in terms of sine and cosine. All right, and then another one is to ask yourself, can your expression be factored? So can you factor? Either using a GC, like by pulling out a common factor, a GCF, or making a box to factor, like a trinomial, which we learned about back in algebra and algebra 2. Okay, so for this first one, I'm going to rewrite everything in terms of sines and cosines, because if I think about factoring, there's nothing in common between these two terms. Okay, so cosecant is the reciprocal of the sine, so I can write that as 1 over the sine of x minus, this is already a cosine, I'm going to leave that alone, and then cotangent of x. Now, I know cotangent is the reciprocal of the tangent. I could write 1 over tangent, but my tip was to rewrite things in terms of sines and cosines. So if you look in the section that says quotient identities, remember that tangent was the same as sine over cosine. Well, cotangent is the same as cosine over sine. Right now, the argument in all of these is u, because when I made this sheet, however long ago, whatever book I was using, they used u's and v's for the angles. This can be any angle. Like you could use x's, you could use thetas, it doesn't matter. So I don't want that to trip you up. That just means whatever angle you're referring to. In this case, we're using x's. So cotangent is the same as, what do we say? Cosine over sine. All right, so then I'm going to simplify. This I can multiply across the top and across the bottom. So I'm going to have 1 over the sine of x minus cosine x times cosine x is going to be the cosine squared of x. So I'm going to write it like this, cosine squared of x, and then 1 times sine of x is sine of x. Now, with this right here, when I have, like I said, cosine of x times cosine of x, my notation is going to put the squared right there. Because if I were to write it like this, it would seem like just the angle is being squared. So if like my angle is 30 degrees, it would look like more like cosine of 30 times 30, which is 900, instead of the cosine of 30, whatever that value is, times the cosine of 30. So instead of saying, root 3 over 2 times root 3 over 2, it means something totally different. Okay, so this is going to be our notation. All right, so now I have a common denominator. So we're going to be using a lot of arithmetic rules, operations, working with fractions and things like that. But instead of having numbers, we have these trig expressions. Okay, so when we add or subtract things with a common denominator, we keep the denominator. And then on top, we have 1 minus cosine squared of x. All right, so now I'm going to look on my identity sheet and see if I see any identity relating a 1 that has a 1 minus cosine squared x in it. Okay, so nothing up here, nothing up here. I want you to look in this section that says Pythagorean identities, and there are 3 of them there. Okay, so we've got 3 of them. We've got that the sine squared, I'm going to write it as the sine squared of x plus the cosine squared of x equals 1. Okay, and then we've got 1 plus tangent squared x equals secant squared x, and then I've got this 1 plus cotangent squared x equals, I'm just going to write x's because most of our stuff will have x's or thetas versus u's. Okay, we have those 3. So when you're looking at them, does any of them contain a 1 and a cosine squared? Oops, this is supposed to have an x on it. Okay, because I want another way to write that 1 minus cosine squared x. So this Pythagorean identity here, in particular this one is going to come up a ton. This idea that sine squared plus cosine squared equals 1. Now from this, I can get 2 bonus identities. If I were to take this and I were to take it and I were to solve for the sine squared of x. So if I were to subtract the cosine squared from both sides, I would end up with that sine squared x equals 1 minus cosine squared of x. So that's kind of a bonus identity. So this is like the mothership, right? And then we've got this extra one that we get off of it. Okay, now there's a second identity I could get off of this, a second bonus. If I were to take this starting identity and I were to subtract the sine squared of x from both sides, I would get that the cosine squared of x equals 1 minus the sine squared of x. Right, these 3 are going to turn up in things regularly. We see it actually happening right now, right? That the 1 minus cosine squared is equal to sine squared of x. And so I can swap this out for sine squared of x. So I have sine squared of x over the sine of x. And then I'm almost done. I can reduce that, right? If I have sine squared x over sine of x, that's like I had sine x times sine x over a sine of x, and one of those cancels. Okay, so that just leaves me with the sine of x. So when you're asked here to simplify, like I took this whole thing, right? It looks kind of like a mess, and it just ends up equaling sine of x. And that's kind of our goal in these, is to kind of condense them down using all these identities. So take a look at the next one. And remember the 2 tips that I've given you, right? Rewrite everything in terms of sines and cosines, and then could you factor? It really doesn't matter the order you do these in. I do notice that both of these terms have a sign of x in them. And so I might start by pulling out a greatest common factor of sine of x, and then think about what would be left inside the parentheses. Okay, again, remember, as I'm doing these, you should pause. So if I say, okay, hey, do this to start, then you should pause and see what happens when you do it, and then try to go from there. So sine times what would give me sine? This would be 1 plus sine times what would get me back to sine cotangent squared. So this would be cotangent squared of x. Okay, now when I'm saying this, I know a lot of times I'm just saying sine and saying cotangent squared, and I'm not saying the x, but I always write it. Okay, you have to have that argument. It's like you would never just say the square root of and not have something in there, a number or a variable, right? It's the same thing with saying cosine or sine. It's of something. You have to have that something. Okay, so now that I'm taking a look at this, I've got 2 things I could do. I could rewrite this in terms of sines and cosines, or I could look on my identity sheet and see if there's anything that's equal to this 1 plus cotangent squared of x. So when I'm looking at my identity sheet and like including, I've got all these bonus identities here, I see 1 plus cotangent squared is right here. It's equal to the cosecant squared of x. So in place of this, and I've got sine of x times cosecant squared of x. And now I'm going to go for write this as in terms of sines and cosines. So cosecant squared is the same as 1 over sine squared. And you might say, I don't see that on there anywhere. And you don't see that on here anywhere. But for all of these up here, if you were to square both sides, right, then that gives you another equivalent identity. So if I were to take that I know the sine of x equals 1 over the cosecant of x. And if I were to square both sides, I'd get sine squared x equals 1 over cosecant squared x for any of them, right? The same idea. So really from all these, if I do the same exact thing to both sides, that equivalent identity equation is another identity. Okay, so that's basically what I did right here. And then I can reduce that fraction because I have now sine of x over sine squared of x. And so I can reduce this. I have 1 here and I have 2 here. So this is like having 1 over the sine of x, which I could then take back to cosecant of x. You're probably like, do I really have to do that? Kind of depends on the directions. If it says like try to write it as a single trig function, you'd really want to go this far. Sometimes it might just say rewrite in terms of sines and cosines, and then that would be okay. Really, you want to try to write it with the least number of symbols possible. Okay, so we probably would want that. When we get into the next section, it actually the answer is kind of within the problem, and so you kind of will know better how far to go. All right, so this next slide, I just have a bunch of examples that I'm going to go through all of them. I would say try them as best you can on your own. And then if you get stuck, watch the video, pause it, and then try and go from there. The thing with these is like don't always start them all the same way. It's not like, okay, I do the same step every time, and sometimes people get frustrated with that. Okay, so looking at C, I notice there's a cosine squared as part of both of them. There's more than one way to go about these two, so just keep that in mind also. There's way more than one way to do these and be totally right. So just kind of go with what do you think your first gut instinct would be, and the more you do them, the easier it gets. Okay, so I look at that and say, I see cosine squared as part of both of them. I just don't want you guys to think that, I did it this way and then you didn't think of it that way and that I'm right and you're wrong. Okay, you could have thought of a totally different way and be completely right. I just happen to notice this. So if I pull a cosine squared out of both of them, I'm left with tangent squared x plus 1. And then I'm looking at my sheet. Is tangent squared 1 plus tangent squared x equals something? Oh, that was one of my Pythagorean identities. Those come up a ton. I noticed that equals secant squared. So cosine squared x times secant squared x. Well, those are reciprocal functions of each other, right? Secant squared is the same as 1 over cosine squared. So then that's cosine squared over cosine squared, which is 1. So that would be one way to go about it. Another thing that you might have noticed, or you might have done where, okay, I'm going to rewrite in terms of sines and cosines. So if I did that, the tangent squared, so we know tangent is sine over cosine. If I square both sides, that means tangent squared is sine squared over cosine squared. So let's say you notice that. Okay, when you go to simplify here, these cancel. So you're left with sine squared x plus cosine squared. Well, that's one of our identities. That is equal to 1. So you see there's more than one way to get that answer and be totally right. Okay, so part D. All right, part D, I look at that and okay, I'm just, nothing to factor. It's all one term. So that just makes me want to rewrite anything that's not a sine or a cosine in terms of sines and cosines. Sometimes it helps me to put the little dots to kind of see. There. It's all one term, but to kind of see each part of the term separately. All right, then I notice, okay, well, this is on top and bottom. Those guys go. These guys go. 1 times cosine x is just cosine x. That one wasn't too bad. I don't know if there's a faster way on that one or a different way, really. That'd probably be it. Okay, part E. Part E. So looking at those, I see I have 2 different terms. They each have something with them, but no common factor. So I'm thinking, okay, anything that's not a sine or cosine, I'm going to rewrite it as a sine or cosine. So tangent is sine over cosine. Keep that sine. Cotangent is cosine over sine. Again, I know I'm just saying cosine over sine, but notice I'm always writing those x's. Okay. Let's see here. Anything I can simplify. These cancel. These cancel. So I'm left with sine of x plus cosine of x. And then you are done. Okay. If we were in class, there would be people that would say that answer is 1. And the way they would get that the answer is 1, let me show you, because it happens all the time. This is done, though. Here's what people would think. They would say, okay, this is an identity. And they would take the square root of both sides. And they would say the square root of this is this. And the square root of this is this. And so that means that has to equal 1. But is this true? Does the square root of this equal just sine x plus cosine x? Think about this. If you had the square root of 9 plus 4, would you say that equals the square root of 9 plus the square root of 4, which would be 3 plus 2, which is 5? I hope not, right? Because technically this is the square root of 13. These aren't the same. You can't split that radical over the two different terms to get your answer. This is not true. Okay, as much as some of you want to think that it's true, it just is this. So just leave it alone. It's really easy to get sucked into that trap. All right, so let's take a look at part F. Part F, fractions, great. Fractions, already sines and cosines, nothing I can do with that. All right, so I'm going to have to add these. And so what I'm going to do is I'm going to get a common denominator. And back last year, you did things with rational functions and you talked about getting common denominators. If you had something like 2 over x plus 3, and then let's say plus 5 over x plus 2, and I said get a common denominator, remember what you did, or in general, when you're stuck getting common denominators, like if this was a 5 and this was a 7, you would multiply 5 and 7 and say your common denominator is 35. Okay, if you have expressions, you would just say your common denominator is x plus 3 times x plus 2. And then you would say something like, well, to get this to turn denominator turn this denominator, I have to multiply top and bottom by x plus 2. And then to turn this denominator into this, I'd have to do top and bottom by x plus 3. Okay, same idea we're going to use here, except trig functions. It'll be okay. So our common denominator is going to be 1 plus cosine of x times 1 minus cosine of x. Now, again, last year, you saw the relationship between these. They're called conjugates. And you did a little with conjugates last year when you were doing complex numbers, right? You'd have 2 plus 3i, and we talked about the complex conjugate was 2 minus 3i, where you took the opposite of that imaginary part. These are called conjugates, not complex conjugates, but conjugates. And we're going to use this idea of conjugates on and off here. Okay, to turn this denominator into this denominator, I have to multiply the top and the bottom. So this has got a 1 plus cosine of x. It needs to have a 1 minus cosine x multiplied to the top and the bottom. To turn this denominator into this new denominator, this needs to be multiplied by 1 plus cosine of x to the top and the bottom. So now, when I add across the top, I have 1 minus cosine x times the sine of x. I'm going to put the sign in front. It's sometimes easier to see that distribution. Plus this sine of x times 1 plus cosine of x. Okay, so this is where that came from, right? And then all my highlighters out here. This is where this came from. And then this is my common denominator here that I just write the one time. Okay, so now I'm going to get rid of all those parentheses. So here I'm going to distribute. So here's where I would, if I were you, pause and work it out yourself and see what you end up with. So I have sine of x minus sine x cosine x. And then here I have plus sine of x plus sine x cosine x all over. Okay, this guy here, we have to multiply that out. You could make a box to do the multiplication if you want. We learned this last year, or in algebra, 1 plus cosine x times 1 minus cosine x. So this would be 1, that'd be cosine x minus cosine x minus cosine squared x. So the idea with the conjugates, and this always happens, and is one of the reasons why we'll use this trick sometimes, is it's like those middles that those guys cancel out. So I'm left with 1 minus cosine squared x. Okay, on top, See, is there anything that goes away? These are opposites. They're gone. I've got sine of x plus sine of x. They're being added, not multiplied. So that's 2 sine of x. And then 1 minus cosine squared of x. I want to look on my identity sheet and see what I've got. So here's my identity sheet. And then here on this card, I have my bonus identities. You might want to jot these bonus identities onto your identity sheet, just so that you have them, like all in one spot. So what am I looking for? 1 minus cosine squared x. Sine squared of x. Nice. Okay, sine squared of x. These reduce, right? I've got a sine of x here, and this is like having sine x times sine x, so one goes away. So I have 2 over sine of x. Or you could think of this as, I'm going to come over here, 2 times 1 over the sine of x, which is 2 cosecant of x. Really, I think the 2 over sine of x is fine. The 2 cosecant of x is fine. And like I said, when we get to the next lesson, the answer is kind of embedded in the problem and makes it easier to tell when you're done. Okay, one more. So this last one is in terms of sines and cosines, so I can't, rewrite anything. Sort of like in the last one, there was nothing to rewrite. I see like these two both have cosine squareds, these two both have sines in them, but I don't have anything that has all of them. And so remember we talked about factoring with the box or with factoring out of GCF. And in this one, because it's a trinomial, it has 3 terms, we're going to factor with a box. We're going to go right to the box. If you want to switch the thetas into x's, because sometimes the thetas just kind of loopy, go ahead. Okay, so remember when you use the box, your first term goes in the top left, your last term goes in the bottom right. This diagonal has to add to be your middle term. So it has to add to be 2 cosine squared. I put an x there, even though I was using thetas. Force a habit. Sine squared theta. And it has to multiply to be the same as this other diagonal. So if I multiply these together, I get cosine to the 4th theta sine times sine to the 4th theta. Okay, that's just always the rule when we factor with the box. Right? The diagonals have to multiply to be the same thing. This diagonal has to add to be your middle. So you want to think about what terms will multiply to be cosine to the 4th, sine to the 4th, but then add to be this. So I know that these terms here, because they have to add to be cosine squared, sine squared, these two terms have, the variable part is cosine squared, sine squared. So these both have to be cosine squared, sine squared. And I want them to add to be 2 cosine squared, sine squared. Oh, look, they do. One of these plus one of these is 2 of these. And think about it, if you multiply these together, it would be cosine to the 4th, sine to the 4th. How we figure out the outside of the box is we pull a GCF. So from this row, I notice this is cosine to the 4th, this is a cosine squared. I'm going to pull cosine squared out. And then I'm going to think cosine squared times what is cosine to the 4th? Another cosine squared. And I'm going to think this times what would get me here? I would need a sine squared. And then cosine squared times what would get me here? I need a sine squared. And then this times this, if you did it right, should end up being your last box. So your factors are cosine squared theta plus sine squared theta. Well, times cosine squared, they're the same thing twice, so I could just write this squared. All right, now is there anything I can do with that? We did all that work. Remember, this is your big Pythagorean identity, right? Sine squared plus cosine squared is 1. So that's just 1 squared, or 1. All right, so this whole big thing here, just equal to 1. Okay, and that's what we're kind of practicing with today. And then the next lesson, we're going to do more practice with this. And it's going to be that we're proving identities. I know the word proof is not always your favorite in math, but we're going to be proving identities. And it will actually kind of be easier. Okay, take care, pre-calculus students.